Welcome back. We're done with the midterm, so we are ready to start off in the second half of the course. We're going to be looking at normal distributions and hypothesis testing. Okay, so let's pick up from where we left off before the midterm exam. We finished up the first half of the course by talking about probability distributions in lesson 12. And then we looked at a specific type of probability distribution in lessons 13 and 14. That would be the binomial distribution. Now, the binomial distribution is an example of a discrete distribution, meaning it's a distribution of a discrete variable. With discrete variables, only specific values are possible. So, for example, in this graph, I have a binomial distribution where you can get values between 1 and 11. Possibly 0 and 12, but those probabilities in this particular graph are so small we can't even see. So essentially, you can only have values 1 through 11, but the point is whole number values. We're not talking about any in-between numbers. Good example of this would be the number of siblings you have. You can have 2 siblings, you can have 4 siblings, you can have 7 siblings, you can have 10 siblings, but you can't have 8.5 siblings or 2.376 siblings, okay? We're talking about whole numbers. Here's another example of a discrete variable. This would be rolling a single die. If you roll a 6-sided die, you can only have one of 6 possible outcomes. And so since it's 1 out of 6, that means the probability of each number is 1/6, 16.67%. And so the probabilities are the same across the board, across all your probabilities. So the probability distribution of rolling a die is going to have the same probabilities for all 6 categories. Now, this makes it really nice because if you want to calculate the probability of a single specific value, you just look in your probability distribution table and just add up that, or just look at that single value. Or if you're looking at a graph, what's the height of the graph? Calculating the probability of a range of values is also easy. For example, if I say, well, what's the probability of rolling a 1, 2, 3, or 4? Well, remember from lesson 9, that's an OR probability. Probability of 1 or 2 or 3 or 4. And what does OR mean? It should mean addition. So what's the probability of 1 plus the probability of 2 plus the probability of 3 plus the probability of 4? So I can look up those 4 values in a table and add them up, or I can look at the height of the 4 bars in my graph, add them up as well. Okay, so dealing with discrete distributions is quite easy, both for specific values and a range of values. This changes when we get to a continuous distribution. Now, this bottom graph, I have a continuous uniform distribution. By that, I mean that somehow our die becomes magical and we can now roll values in between each value. Okay, so I start with this bar chart saying I can only have specific values, but hey, maybe I'm going to split those in half, and now I can get half values or quarter values or third values. Pretty soon, these bars are getting narrower and narrower and narrower. And if these bars get infinitesimally small, well, we've got a problem. It becomes very hard to calculate the probability of a specific value. Okay, calculating the probability of a specific value gets very difficult because there are an infinite number of bars. And what's the probability of getting exactly one value? Here's a good example. Somebody's weight. Let's say we are measuring people who declare themselves to weigh 160 pounds. What is the probability of somebody who weighs exactly 160 pounds, as in 160.000000? It's going to be extremely small because given on the time of day and the person, people might weigh 160.3 pounds or 161.7 or 159.3, or they are often off by a little bit. And we just say, hey, I'm 160 pounds. This is the idea of a continuous variable, and it makes it very hard to calculate probabilities because probability of one specific value is very, very small. Okay. However, we can still calculate the probability of a range of values. And that's what we're doing here. We're looking at the probability of rolling anywhere between 0.5 and 4.5. Basically, anything between a 1 and a 4. And what's that probability? Well, from our discrete distribution, we decided it was 4 times 0.16667, right? This plus this plus this plus this. Just the 4 columns added up together. With a continuous distribution, we're going to see the same probability. Basically, our curve, in other words, the top of our probabilities, we're going to call that now a density function. I'm sorry, I have some math here. This is the probability for the discrete distribution of rolling either 1, 2, 3, or 4. There's the math for it. We're going to need that. For the continuous distribution, the height of the bars is no longer the probability, but we call it a density function. That would be the function that gives the top of this distribution here. And this density function is going to help us because that gives us a height of an area. And if we take a width of that area, what do we get? Well, the height of this area here is 0.16667, and it has a width of 4. Well, what's 4 times 0.1667? That's 2/3. That's the same probability we had with our discrete distribution. Okay, here's the point. With discrete distributions, you add up all of your columns or all of your different categories together. We can't do that with a continuous variable, but we do with a range of variables. And how do we calculate the probability? We calculate the probability by finding the area under our density function. And that's how we're going to deal with the rest of the semester, really. We're getting into normal distributions and finding probabilities there. We're going to do it by finding the area underneath the density function.